Welcome back. Lecture 3 of this week will take a small detour away from the properties of subsequences, but focus on an application of subsequences for classifying sets of real numbers. We will in this lecture introduce the notion of closed subset of real numbers. You're all already familiar with the ideas of open intervals and closed intervals, and you are all somewhat aware of the distinction between the two. For example, one obvious difference is that an open interval has no maximum nor minimum, but a closed interval does. The idea of closed subsets of reals is a way to formalize some of the most useful properties of closed intervals. We will take as our defining property for closed subsets a property about how sequences and subsequences behave. This may seem like a roundabout way of making a definition. Indeed, in other contexts, you may see other ways of defining closed subsets. Rest assured that insofar as subsets of real numbers go, all the various notions are equivalent, meaning that if you take any of the definitions as the definition, you can always prove that the other definitions are satisfied. To put it another way, one person's definition may be another person's theorem. But by the way, the fact that different people can come to the same conclusion starting from different premises is not something that is unique to mathematics. In mathematics and in life, make sure to always examine the underlying assumptions when trying to hold a dialogue. Many times when people talk past each other, it is simply an issue of incompatible assumptions. Anyway, enough digression. Let's return by showing you the definitions. In this class, we will take the following definition for a set to be closed. This idea is a bit complicated, so bear with me while I try to explain. We will be defining the notion of closed subsets somewhat indirectly. Instead of saying what the set does, we will be giving a descriptive definition in terms of what sequences do in relation to closed subsets. So, start with a set S. Imagine a sequence of whose terms are limited to being elements of S. Now, this sequence may have some subsequential limits. For a general set S and a general sequence, the subsequential limit may or may not be in S. For example, in the final example from lecture 2, we have a sequence whose terms are all rational numbers, but it has subsequential limits which are irrational. This means that if a set S is such that regardless of what sequence you start with, the subsequential limits of that sequence must still remain S, this makes the set S a bit special. These are the sets that we call closed. So again, more formally, the property that defines a closed set is that given any sequence whose terms are restricted to be elements of S, any of its subsequential limits must still be an element of S. In other words, closed sets are those that you cannot escape from by taking subsequential limits. Given this complicated definition, you may ask, are there even any closed sets? A very simple example is the case of the set of one element. That S be a set containing only one number. The number doesn't matter, but for concreteness, call it 13. When I claim you cannot escape from S by taking subsequential limits, why? If a sequence is such that its terms are all in S, then since S has only 13 as an element, this means that every term of the sequence is the number 13. And this also means that every subsequence is also the constant sequence 13. And hence, the only possible subsequential limit of the sequence is the number 13. And there we have it, a set for which the subsequential limits of any sequence valued in S are themselves in S. Let's give some less trivial examples. As I mentioned in the introduction, The idea behind closed set is to capture the essence of the quality of being a closed interval and consider what other sets have the same quality. So it better be the case that our definition does not rule out a closed interval. I mean, if that were the case, we would have made a really unfortunate and confusing choice of terminology. So let's first verify that any closed interval from A to B is a closed set. Start by taking an arbitrary sequence x sub n, all of whose terms are in the closed interval AB. In order to show that all of its subsequential limits are in the interval, it is enough to show that any number outside the interval cannot possibly be a subsequential limit. To do so, we observe that if z is outside of the interval, then either z is less than a or it is greater than b. Depending on which case it is, we choose epsilon appropriately to be 1/2 the distance from z to the appropriate endpoint. Notice that the distance is positive. This is where we use the property that the interval is closed. Because the interval is closed, the points A and B themselves are within the interval. So any point outside the interval would have a positive distance from the interval. If we were working with an open interval instead, then morally speaking, A and B are both numbers outside the interval, which are distance 0 from the interval. And the same argument presented here won't work anymore, because for this argument, we need to find epsilon positive. Now, coming back to the proof. Then, since epsilon is 1/2 the distance, this means that no point in the interval AB is within epsilon distance of z. And since x sub n has all its terms within the interval AB, exactly 0 terms of the sequence is within epsilon distance of our point z. And hence, there are definitely not infinitely many terms of the sequence near z. And by our theorem from lecture 2, z is not a subsequential limit. So with this, we have verified that our notations are consistent, and the closed interval AB is indeed a closed set. Notice that we never required in this example that A is less than B. When A is equal to B, the closed interval from A to B is the set that contains exactly one element, which is A. The proof here also works to show that this set is a closed set. You may wish to pause this video briefly to contrast the proof just given against the proof that a singleton set is closed given in the discussion of the previous slide. Next, we show that the open interval from A to B is not closed. Since the condition for the set to be closed requires every sequence be such that all subsequential limits are in the set, to prove that a set is not closed requires only finding one sequence for which one subsequential limit is not in the set. We can do this explicitly for the open interval. I choose the terms x sub n to be equal to A plus the quantity B minus A over the quantity n plus 1. The form of this sequence is chosen to guarantee that x sub n is inside the open interval. Indeed, x sub n is greater than A since the fraction in the definition is positive. And since the fraction b minus a over n plus 1 is always smaller than b minus a, we conclude that x sub n is always less than b. So with this step 2, we wrote down a sequence whose terms are in the open interval from a to b as required. To conclude the proof, we need to show that this sequence has a subsequential limit that is not in the open interval. Our sequence x sub n in fact converges, and it converges to A. Since A is not an element of the open interval from A to B, this gives us a sequence whose elements are in the interval and who possesses a subsequential limit that is not in the interval. And this shows that the open interval from A to B is not closed. At this juncture, I want to make a remark that open and not closed do not mean the same thing. A set may be both open and closed, and a set may be not closed and also not open. Do not, I repeat, do not take open as the opposite of closed. It is not. The method that we used to prove that the closed interval is closed can be vastly generalized. This theorem describes a method with which we can show that the subset S is closed. The theorem says A subset S is closed if and only if, for every Z not in S, there is a positive epsilon such that no element of S comes within epsilon distance of S. In other words, a subset S is closed if and only if every point that is not in S is separated from S by a gap. Notice that the order of the quantifiers. The epsilon, which measure the size of the gap, is allowed to depend on the point Z in question. We do not require a uniform gap that applies to all points not in S. Rather, the size of the gap is expected to depend on the Z you are looking at. The situation being ruled out by this condition is like what happened for the open interval, where we have a point that is basically attached to the set but not quite in it. Let's give proofs. First, we prove the implication that every Z is separated from S by a gap implies that S is closed. The proof is essentially a rehash of our proof for the closed interval case, so I'll go through this quickly. If Xn is a sequence of whose terms belong to S, and Z a point outside of S, by our hypothesis, there is a gap of size epsilon around Z in which there are no elements of S. Since x of n has terms all being elements of S, this means that there are no terms of xn within this gap, and this shows that Z cannot be a subsequential limit of x of n. For the proof that a closed set has the property that every Z outside is separated from S by a gap, we will argue by proving the contrapositive. In other words, we will prove that if there is a point Z outside of S such that there is no gap from Z to S, then there is a sequence whose terms belong to S that has at least one subsequential limit that does not belong to S. So let us start by supposing Z is not in S. The statement that there is no gap from Z to S is formalized as the negation of the condition given in the theorem statement, which now reads that for every positive epsilon, the interval from Z minus epsilon to Z plus epsilon contains some element of S. This means we can build a sequence by hand. Given an index n, set epsilon to be 1 over n. Then, by step 1, within the interval from Z minus 1 over n to Z plus 1 over n, there is some element of the set S. There may be multiple, but we know there is at least one. So we can choose one of them and set x sub n to equal it. This means that we have constructed x sub n such that every term is an element of S. To show that S is not closed, we need to show that there is a subsequential limit of x sub n that is not an element of S. It turns out, however, for the xn we just built, it converges to Z. For every epsilon positive, by the Archimedean principle, there is a capital N such that epsilon is bigger than 1 over capital N. But then, for any further term, since we know that x sub small n is selected from the interval z minus 1 over n to z plus 1 over n, this means that the difference of x sub small n to z is no more than 1 over small n, which, when small n is bigger than capital N, is less than 1 over capital N, and which in turn is less than epsilon. Since epsilon is arbitrary, this shows that the sequence x sub n satisfies the condition for convergence to Z. So, to conclude, assuming that there is a point in Z outside of S that is basically touching the set S, we are able to build a converging sequence whose terms are all in S and whose limit is outside of S, showing that S cannot be closed. Okay, that's it for this lecture. See you next time.